Learn Isotonic regression. Description: Isotonic regression is a non-parametric regression model in scikit-learn that enforces monotonicity on the predicted output. This means that the predicted values must either always increase or always decrease as the input values increase. Inputs: X. The input features independent variables. It can be a one-dimensional array or a two-dimensional array where each row represents an observation and each column represents a feature. Y. The target values dependent variables. It must be a one-dimensional array. Outputs: Y. The predicted target values. It is a one-dimensional array of the same length as Y. Isotonic. The fitted isotonic function. It is a one-dimensional array that represents the fitted relationship between the input values and the predicted target values. Steps: the model first calculates the cumulative sum of the input values. Then, it calculates the cumulative sum of the target values. Using a pool adjacent Violatus-Bow algorithm, it finds the optimal monotonic relationship between the cumulative sums of the input and target values. Metrics: R-squared, a measure of how well the model fits the data. It ranges from 0 to 1, with 1 indicating a perfect fit. Mean squared error MSE, a measure of the average squared difference between the predicted values and the actual values. Visualization plots: scatter plot, a scatter plot of the input values against the predicted target values. This plot can help visualize the monotonicity of the fitted relationship. Fine-tune parameters: Y min, the minimum value of the predicted target values. Y max, the maximum value of the predicted target values. Increasing, a Boolean flag that indicates whether the fitted relationship should be increasing or decreasing. Out of bounds, a string that specifies how to handle out of bounds input values. Uncertainty methods: bootstrap resampling, the model can be fit multiple times on different bootstrap samples of A data to estimate the uncertainty in the predicted values. Confidence intervals: the model can be used to calculate confidence intervals for the predicted values. Challenges and fixes. Challenge 1: overfitting too noisy data. Sample use case that resulted in challenge 1: if the data is very noisy, the model may overfit to the noise and produce a highly non-smooth relationship between the input values and the predicted target values. Fixes to challenge 1: use a smoothing technique, such as a moving average, to smooth the input values before fitting the model. Use a regularization parameter to penalize model complexity. Challenge 2: handling outliers. Sample use case that resulted in challenge 2: outliers can significantly affect the fitted relationship. Fixes to challenge 2: remove outliers from the data before fitting the model. Use a robust regression technique, such as the Theil-Sein estimator, which is less sensitive to outliers. Learn Isotonic check increasing. Description: explain in detail. The check increasing method is a utility function within scikit-learn's Isotonic regression module. It's designed to validate whether a given input sequence is monotonically increasing. This is crucial for isotonic regression, as it ensures that the fitted model produces a prediction that adheres to the assumption of a non-decreasing relationship between the input and output variables. Inputs. Input 1: explain in detail why this input represents the sequence of values that need to be checked. For monotonicity, it can be a NumPy array or a list of numerical values. Input 2: explain in detail. Increasing this Boolean argument specifies the direction of the expected monotonicity. If true default, the function checks for a strictly increasing sequence. If false, It checks for a strictly decreasing sequence. Outputs. Output 1 explain in detail is increasing a Boolean value indicating whether the input sequence is monotonically increasing or decreasing, depending on the increasing argument. If the sequence is strictly increasing or decreasing, it returns true, otherwise, it returns false. Steps. Step 1 explain in detail the function iterates through the input sequence y. Step 2 explain in detail for each consecutive pair of values. It compares them based on the specified direction increasing or decreasing. If the comparison fails to satisfy the monotonicity condition, e.g., a decreasing value is found in an increasing sequence, the function immediately returns false. Metrics. Metric 1 explain in detail there are no specific metrics directly associated with the check increasing method itself, as it's primarily a validation function. However, the success of isotonic regression, which relies on this function, can be evaluated using metrics like mean squared error (MSE), R-squared, and others. Visualization plots. Visualization plot 1 explain in detail a simple scatter plot of the input values y against their indices can be used to visually inspect the monotonicity of the sequence. Fine-tune parameters. Parameter 1 explain in detail the increasing argument can be adjusted to check for either increasing or decreasing monotonicity. Uncertainty methods. Uncertainty method 1 explain in detail this method doesn't directly involve uncertainty quantification, as it's solely a validation function. Challenges and fixes. Challenge 1 explain in detail the check increasing function assumes that the input sequence y consists of numeric values. If the sequence contains non-numeric elements, such as strings or objects, the function will likely fail. Sample use case that resulted in challenge 1: a user might inadvertently provide a sequence containing mixed data types, including strings. This could lead to an error during the comparison of values. Fixes to challenge 1 ensure that the input sequence y consists entirely of numeric values before calling the check increasing function. This can be achieved by filtering out non-numeric elements or by converting the sequence to a numerical representation. Challenge 2 explain in detail if the input sequence contains duplicate values. The check increasing function might not be able to correctly identify whether the sequence is strictly increasing or decreasing, depending on the intended behavior. For instance, if the input is 1, 2, 2, 3, it might return true for both increasing and decreasing sequences. Sample use case that resulted in challenge 2: a user might provide data where certain values are repeated, leading to ambiguity in the monotonicity check. Fixes to challenge 2 in cases where duplicate values are present. Consider whether you need to define strict monotonicity where each value must be strictly greater than the preceding one, or allow for non-strict monotonicity where values can be equal to their predecessors. If strict monotonicity is desired, remove the duplicate values before using check increasing. Otherwise, clarify your expectations about the handling of duplicates. sklearn, isotonic regression. Description explain in detail. Inputs. Why the target values to be made monotonic. It's a 1D array of real values. X the independent variable. A 1D array of real values. Defaults to none, in which case the index of y is used. Y isotonic the isotonic regression output. A 1D array of real values. It's the monotonized version of y. Y isotonic fit the fitted isotonic regression function, which can be used to predict new y values for given x. Steps. The algorithm finds the best monotonic fit to the data by minimizing the squared error between the original y values and the fitted isotonic regression function. It uses the pool adjacent violators algorithm power to achieve this. Metrics. Mean squared error MSE measures the average squared difference between the original y values and the fitted y isotonic values. R squared measures the proportion of the variance in y that is explained by the fitted y isotonic values. Visualization plots. Scatter plot of original y vs fitted y isotonic shows the relationship between the original data and the monotonic fit. Line plot of the fitted isotonic regression function visualizes the trend of the monotonic fit. Y-min lower bound on the output, which can be used to enforce a minimum value on the fitted y isotonic. Y-max upper bound on the output, which can be used to enforce a maximum value on the fitted y isotonic. Bootstrap resampling can be used to estimate the uncertainty in the fitted y isotonic values by generating multiple fits on different subsets of the data. Bayesian methods can be used to incorporate prior information about the monotonic relationship into the model and estimate the posterior distribution of the fitted y isotonic values. Challenge 1. Handling ties in the input X. Sample use case that resulted in challenge 1. If there are multiple input X values that have the same value, the algorithm might produce non-monotonic output. Fixes to challenge 1. Use a different sorting method for X that preserves the order of ties. Challenge 2. Handling extreme outliers in the input Y. Sample use case that resulted in challenge 2. Outliers in the target values can significantly influence the fitted Y isotonic values, leading to a poor fit. Fixes to challenge 2. Remove outliers from the data before fitting the isotonic regression model or use a robust regression technique.